January 6, 1976. The Kola Peninsula. The snow fell in silence over the frozen tundra, each flake dissolving into the white expanse that stretched endlessly beneath the pale Arctic sky. At the edge of the Barents Sea, where ice met water in jagged formations, the cold was not merely felt, it was absolute, a numbing presence that penetrated steel and bone alike. Inside the concrete bunker of the Olenia Air Base, Senior Lieutenant Viktor Petrov sat before his console, watching the green sweep of the radar screen paint its eternal circle. The phosphorescent line passed over the grid again and again, hypnotic in its regularity, revealing nothing but the occasional ghost echo of a fishing vessel or civilian transport. His breath formed small clouds in the inadequately heated room. Outside, the temperature had fallen to -38 degrees Celsius. Inside, it hovered just above freezing. Petrov had been stationed here for 14 months. He knew every flicker of the screen, every pattern of the northern skies. He had watched MiG-25 interceptors scramble on false alarms. He had tracked Norwegian maritime patrol aircraft maintaining their respectful distance from Soviet airspace. He had logged countless hours of monotony, punctuated by brief moments of elevated readiness that always dissolved back into waiting. But on this particular morning, as he sipped his lukewarm tea from a chipped enamel cup, he did not know that 12 miles above the Norwegian Sea, moving at 3 times the speed of sound, an American SR-71 Blackbird was about to make his most sophisticated equipment appear as primitive as a child's toy. The radar screen showed nothing. It would continue to show nothing. And in that absence, in that technological silence, lay a truth that would haunt Soviet Air Defense Command for the next 2 decades. This was not the first time. It would not be the last. But it was one of thousands of flights that revealed an uncomfortable reality. The most advanced radar systems the Soviet Union could deploy, systems representing decades of scientific effort, billions of rubles in development, the collective genius of their top engineers, were functionally helpless against a reconnaissance aircraft that flew so high and so fast that it existed in a realm beyond their reach. The Americans called it the Blackbird. Soviet commanders called it something else, proof that the technological gap was wider than anyone dared to admit in official reports sent to Moscow. To understand the magnitude of this failure, one must first understand the promise. Throughout the 1950s and 1960s, Soviet air defense had been a point of national pride, a demonstration that communist science could match and even surpass Western capabilities. The shoot-down of Gary Power's U-2 spy plane on May 1, 1960, had seemed to validate this confidence. An SA-2 surface-to-air missile had reached up and plucked an American reconnaissance aircraft from 70,000 feet, turning what the Americans had believed to be invulnerable altitude into a death trap. Powers had survived the destruction of his aircraft, parachuting into Soviet custody and international humiliation for the United States. Premier Khrushchev had turned the incident into a propaganda triumph, displaying the wreckage in Gorky Park like a trophy, proof that Soviet defenses could penetrate American technological arrogance. But even then, in the moment of that victory, American engineers were already testing an aircraft that would render such triumphs obsolete. The A-12, the CIA's predecessor to the SR-71, had first flown in April 1962. By the time Powers was being exchanged for Soviet spy Rudolf Abel in February of that same year, Lockheed's Skunk Works had already proven that an aircraft could be built to fly higher, faster, and with a radar cross-section so reduced that conventional detection methods would struggle to acquire it, let alone track it long enough to launch an effective intercept. The Soviet response had been predictable. Build better radars, deploy more of them, network them together. The P-14 Tall King early warning radar entered service with its massive Yagi antenna array, capable of detecting targets at ranges exceeding 300 kilometers. The P-35 and P-37 systems followed, long-range surveillance radars that were supposed to provide comprehensive coverage of Soviet airspace. Fire control radars became more sophisticated, their tracking algorithms refined, their power output increased. The entire system was backed by the world's largest air defense force, hundreds of interceptor aircraft, thousands of surface-to-air missiles, a command structure that theoretically could coordinate responses across 11 time zones. It was impressive on paper. In exercises, it performed admirably against simulated threats. But the SR-71 was not a simulated threat. It was a physical impossibility made real, an aircraft that violated every assumption upon which Soviet air defense doctrine had been constructed. The SR-71 did not achieve its invulnerability through a single innovation, but through a convergence of engineering decisions that compounded into something unprecedented. It cruised at 85,000 feet, more than 16 miles above sea level, well into the stratosphere, where the air was so thin that conventional aircraft could not generate sufficient lift or engine thrust to maintain flight. At that altitude, the curvature of the Earth became visible to its two-man crew. The sky above turned from blue to black. Stars became visible even in daylight. The aircraft existed in a realm between atmosphere and space, too high for normal aviation, too low for orbital mechanics. But altitude alone was not enough. The U-2 had proven that height could be overcome by determined adversaries. What made the SR-71 different was speed. Its two Pratt & Whitney J58 engines, each producing 32,000 pounds of thrust, pushed the aircraft to velocities exceeding Mach 3.2, approximately 2,200 miles per hour. At that speed, the aircraft covered a mile every 1.6 seconds. It traversed the width of Soviet radar coverage faster than human operators could coordinate a response. From the moment it was first detected, if it was detected, until it exited coverage could be as little as 4 minutes. Scrambling interceptors, calculating firing solutions, launching missiles, all of these required time that simply did not exist. The physics became even more problematic when one considered the energy requirements for intercept. A MiG-25, the Soviet Union's fastest operational interceptor, could briefly reach Mach 2.83 under ideal conditions, but only in straight-line flight at maximum afterburner, consuming fuel at a rate that gave it minutes of effective combat time. The MiG-31 that succeeded it improved on this, but still operated within constraints that the SR-71 simply ignored. To intercept a target flying at Mach 3.2 at 85,000 feet required not just matching its speed, but exceeding it, and doing so while climbing to an altitude where engine performance degraded and maneuverability became nearly impossible. The equations were brutal. Even if a Soviet interceptor could reach the SR-71's altitude and speed, which it barely could, it would have almost no energy left for maneuvering or combat. A stern chase from behind was physically impossible. The interceptor would run out of fuel before closing the distance. A head-on intercept required predicting the SR-71's exact flight path with enough precision to position the interceptor in its path at precisely the right moment, a task made nearly impossible by the speed at which events unfolded. Then there was the matter of radar signature. The SR-71's design incorporated features that reduced its radar cross-section significantly below what its physical size would suggest. Its titanium construction, necessary to withstand the 600-degree temperatures generated by air friction at Mach 3, had electrical properties that affected radar reflection. Its chines, the sharp leading edges that ran the length of the fuselage, were angled to deflect radar energy away from the emitting source. Special radar-absorbing materials were applied to critical surfaces. The result was an aircraft that, when detected at all, appeared on radar screens as something much smaller than it actually was, often indistinguishable from weather phenomena or electronic noise. Soviet radar operators had been trained to identify targets by their signatures, to distinguish between different aircraft types based on the characteristics of the radar return. But the SR-71 presented a return that made no sense within their framework of reference. It appeared, when it appeared at all, as a faint, fast-moving blip that could be a malfunction, atmospheric interference, or perhaps a meteor. By the time an operator convinced himself that the contact was real and worth reporting, it had often already vanished from his screen. The theoretical scenarios practiced in Soviet training exercises bore little resemblance to the reality of attempting to engage an SR-71. In theory, early warning radars would detect the intruder at maximum range. This information would be passed to command centers, where trained officers would evaluate the threat and authorize a response. Interceptors would be scrambled, guided toward the target by ground controllers using data from tracking radars. Fire control systems would lock onto the target, and missiles would be launched with sufficient lead to intercept the predicted flight path. The entire system had been designed for exactly this purpose, refined through decades of development and billions of rubles in investment. In practice, it rarely worked. The early warning radars often failed to detect the SR-71 at all, their beams either unable to achieve sufficient return from the aircraft's reduced cross-section or unable to distinguish it from background clutter at extreme ranges. When detection did occur, it was frequently intermittent. The target would appear for one sweep of the radar, disappear for several sweeps, then reappear kilometers away from its last known position, making it impossible to establish a reliable track. The speed alone created plotting problems. Human operators and automated systems alike struggled to accept that a target could be moving so fast, often initially rejecting the data as erroneous. Even when a solid track was established and interceptors were scrambled, the geometry of the situation made success nearly impossible. The SR-71 typically entered Soviet radar coverage at the edge of the surveillance zone, flew a predetermined route through the areas of interest, and exited coverage on the far side, all in a matter of minutes. Soviet interceptors, even when already airborne on combat air patrol, needed time to accelerate to maximum speed and climb to intercept altitude. That time was almost never available. By the time a MiG-25 reached the altitude and speed necessary for even a theoretical intercept opportunity, the SR-71 had usually already photographed its targets and was departing the coverage area. There were attempts. Soviet pilots were not cowards, and they understood the importance of defending their airspace. Detailed accounts from debriefings reveal the frustration of highly trained aviators who pushed their aircraft to the absolute limits of performance, who climbed until their engines were gasping for oxygen in the thin air, who watched their fuel gauges plummet as they maintained maximum afterburner, all while the target they pursued remained a radio call from ground control, always ahead, always too high, always too fast. Some pilots reported seeing the SR-71 visually, not the aircraft itself, but its contrail, a distinctive pattern in the stratosphere, taunting them from altitudes they could not quite reach. Missile engagements were equally futile. The SA-2, which had successfully downed Power's U-2, lacked the speed and altitude capability to threaten an SR-71. The SA-5, specifically designed for high-altitude targets, had better performance characteristics, but still struggled with the combination of altitude, speed, and the time compression that the Blackbird's velocity created. To successfully engage a target with a surface-to-air missile required detecting it early enough to calculate a firing solution, launching the missile with sufficient lead time to allow it to climb to the target's altitude, and maintaining radar guidance throughout the missile's flight. Against the SR-71, this sequence rarely completed successfully. The target moved through the engagement envelope too quickly. Radar locks broke. Missiles launched with seemingly adequate lead calculations found themselves behind a target that was pulling away from them, unable to match its sustained speed. There were claimed successes. Official Soviet records mention instances where SA-5 missiles came close to SR-71s over the Baltic and the Barents Sea, where pilots reported achieving radar lock, where ground controllers insisted their systems had functioned perfectly, and that only minor variations in timing had prevented a kill. American records tell a different story. While SR-71 crews occasionally received warnings from their defensive systems indicating that radar had illuminated them or that missiles had been launched, not once in the aircraft's operational history did a Soviet missile or interceptor come close enough to inflict damage. The claims were face-saving, official reports crafted to avoid admitting the uncomfortable truth to superiors who did not want to hear it. There was an irony in the SR-71's construction that Soviet intelligence officers surely recognized, though they rarely spoke of it openly. The aircraft was built primarily of titanium, approximately 93% by weight. This exotic metal was necessary because aluminum, used in virtually all conventional aircraft, would soften and lose structural integrity at the extreme temperatures generated by Mach 3 flight. Titanium could withstand the heat. But in the early 1960s, when the SR-71 was being manufactured, the United States did not produce sufficient titanium for the program's needs. The majority of it was purchased through shell companies and circuitous routes designed to obscure its ultimate purpose from the Soviet Union itself. Soviet titanium, mined in the Ural Mountains and processed in Ukrainian metallurgical plants, was shipped westward, transformed in American factories into an aircraft specifically designed to penetrate Soviet airspace, then sent back east to fly surveillance missions over the very territory from which its raw materials had originated. The circle was complete, the irony profound. Soviet workers had extracted the ore, refined it, and sold it for hard currency their country desperately needed. American engineers had shaped it into something the Soviet military could not stop, and Soviet air defense commanders watched it pass overhead, helpless, while Moscow demanded to know why the intruders had not been shot down. This titanium became more than a material. It became a symbol of the differences between the systems. American engineers had taken a basic element, titanium, atomic number 22, and through innovation, precision manufacturing, and willingness to accept extraordinary cost overruns, had created an aircraft that redefined what was possible. The SR-71 program was ruinously expensive, its unit cost astronomical, its operational requirements demanding. But it worked. It delivered intelligence that could be obtained no other way. It demonstrated technological capabilities that adversaries could not match. Soviet engineers were not lacking in brilliance or dedication. They worked with more limited budgets, under more rigid bureaucratic constraints, within a system that punished failure harshly and rewarded caution over risk-taking. They created impressive systems. The MiG-25 was itself a remarkable achievement, an interceptor that could reach speeds and altitudes that rivaled anything in the Western arsenal. But it was designed to counter bombers, not reconnaissance aircraft. It was optimized for brief sprints to intercept altitude, not sustained cruise at extreme speeds. When asked to perform missions for which it was not designed, it revealed its limitations. The titanium of the SR-71 was machined to tolerances measured in thousandths of an inch, welded using proprietary techniques that Lockheed had developed specifically for the program, assembled by workers who understood that any error could be catastrophic at Mach 3. Soviet titanium was of good quality. It had to be for the Americans to purchase it. But the manufacturing culture, the institutional knowledge, the willingness to accept initial failures as part of the learning process, these were advantages that Soviet industry struggled to replicate. For the Soviet officers who manned the air defense network, the SR-71 flights became a recurring reminder of inadequacy. They knew when the Americans were planning missions. Intelligence sources provided warnings, communication intercepts offered hints. Alert levels would be raised. Interceptors would be placed on heightened readiness. Radar operators would be briefed to watch for the specific characteristics of the target. And then it would happen. a faint contact at extreme range, moving impossibly fast, high above any altitude their systems were truly optimized for. Calls would go out, interceptors would scramble, missiles would be brought to launch readiness. And the target would continue on its path, undeviating, apparently unconcerned with the frantic activity below, photographing military installations, mapping radar sites, collecting electronic intelligence on the very systems that were trying unsuccessfully to engage it. The psychological impact was considerable. Soviet military culture emphasized competence, readiness, the ability to defend the motherland against any threat. Officers who failed in their duties faced career consequences, sometimes worse. Yet here was a threat that appeared dozens of times per year throughout the 1970s and into the 1980s, and the success rate against it remained stubbornly at zero. Reports had to be filed, explanations offered. The truth that the Americans had built something the Soviet system could not effectively counter was politically unacceptable. So, alternative explanations proliferated. The weather had been problematic. The specific flight path had exploited a temporary gap in coverage. If only the missile had been launched 3 seconds earlier, if only the interceptor had been vectored slightly differently. Some officers became obsessed with the problem. They studied every engagement, analyzed every failure, proposed modifications to doctrine and hardware. A few achieved minor improvements: better coordination between radar sites, refined intercept geometries, updated fire control algorithms. But these were incremental gains against a target that operated with such performance margins that incremental improvements made no meaningful difference. It was like trying to catch lightning. You could improve your technique, position yourself more carefully, move faster than before, and you would still fail because the fundamental physics were against you. Others adopted a different philosophy: acceptance. They understood that their equipment and training were designed for different threats: cruise missiles, strategic bombers, NATO fighter bombers at medium altitude. Against these threats, Soviet air defenses were genuinely formidable. The SR-71 was an outlier, an American prestige project, expensive and specialized. Let it fly its missions. The intelligence it collected, while undoubtedly valuable, was largely confirming what American satellites were already photographing from orbit. The real war, if it came, would be fought at lower altitudes by different aircraft, and there Soviet defenses would prove their worth. But even this pragmatic acceptance carried its own bitterness. It was an admission that there were realms where Soviet technology could not compete, altitudes where American aircraft could operate with impunity, a three-dimensional space above Soviet territory where sovereignty was more theoretical than actual. The wider context of competition. The SR-71 situation was not isolated. It was part of a broader pattern that characterized the Cold War competition, a pattern that Soviet leaders found deeply troubling. In submarines, the Americans maintained technological leads in quieting and sensor capabilities that made their boats harder to detect and more effective at tracking Soviet vessels. In precision-guided munitions, in digital electronics, in material science, across multiple domains, the United States demonstrated advantages that were not merely marginal but fundamental. Some of this reflected different strategic priorities. The Soviet Union invested enormous resources in land forces, in ballistic missiles, in quantities that could potentially overwhelm qualitative advantages through sheer numbers. American defense spending, while substantial, was distributed differently, with greater emphasis on technological superiority in specific domains. The SR-71 embodied this approach. A small fleet, never more than 32 aircraft were built, and only a fraction of those were operational at any given time, that delivered disproportionate capability through technical excellence. But there was also a systemic component. Western defense industries operated within a competitive framework that, despite its many inefficiencies and cost overruns, generally rewarded innovation and punished stagnation. Companies that failed to deliver were replaced by competitors. Engineers who proposed radical new approaches found funding if they could demonstrate potential. The SR-71 itself was the product of Lockheed's Skunk Works, a semi-autonomous organization within the larger company that was specifically structured to avoid bureaucratic constraints, where small teams of highly talented engineers worked with unusual freedom to solve problems in unconventional ways. Soviet defense industry was organized differently. Design bureaus competed for contracts, but within a framework that was ultimately controlled by state planning committees and political oversight that prioritized reliability over innovation, proven designs over risky new approaches. The consequences of failure were severe, not just loss of funding, but potential criminal prosecution for sabotage or incompetence. This created a culture that was excellent at refining existing concepts, but struggled with the kind of radical innovation that the SR-71 represented. The titanium welding techniques used in the SR-71's construction had taken years to develop and resulted in numerous failed prototypes before successful methods were established. In the Soviet system, such extended failure would have been difficult to tolerate. The J-58 engine underwent similar trials, with early versions destroying themselves on test stands before the final design emerged. The entire SR-71 program was, in American terms, a controlled catastrophe of cost overruns and technical setbacks that nonetheless persevered until success was achieved. This model of development, expensive, failure-tolerant, ultimately successful, was culturally difficult for Soviet institutions to replicate. What made Soviet helplessness against the SR-71 particularly galling was the intelligence value the aircraft delivered. Each mission returned with thousands of photographs covering hundreds of miles of terrain, with resolution sufficient to identify individual vehicles and track construction progress at military facilities. The aircraft's sensors could map radar installations, record communications frequencies, and collect electronic signatures that would be invaluable in any future conflict. American intelligence analysts knew where Soviet missile silos were located, how many submarines were in port at Northern Fleet bases, which airfields were being expanded, where new defensive positions were being constructed. This information shaped NATO planning at every level. It allowed American targeting specialists to develop detailed strike packages for scenarios that, thankfully, never occurred. It provided warning of Soviet military buildups and technological developments. It offered confirmation or refutation of intelligence collected by other means, serving as ground truth against which satellite photography and human intelligence could be compared. For Soviet military planners, the knowledge that so much of their defensive infrastructure was being systematically documented created enormous complications. Every new installation had to be assumed compromised. Every troop movement had to account for American awareness. Denial and deception became paramount, but these measures were costly and often ineffective against sensors that could see through camouflage and detect heat signatures. There were attempts at countermeasures beyond attempting direct engagement. Some facilities were relocated to areas less likely to be overflown. Mobile systems became more common, harder to track and target. Decoys were constructed to simulate high-value installations. But all of these measures were reactive, acknowledgements that prevention had failed and that mitigation was the only option remaining. The SR-71's operational career ended not because Soviet air defenses finally developed effective counters, but because satellites and unmanned reconnaissance systems eventually offered comparable intelligence with lower risk and operational cost. The last Blackbird was retired in 1998, briefly brought back for research purposes, then permanently grounded in 1999. By then, it had flown missions for over 3 decades, accumulating an operational record that included 0 losses to enemy action, a statistics that spoke volumes about its invulnerability. Soviet air defense, by the time of the USSR's dissolution in 1991, had improved significantly from its 1970s capabilities. The S-300 surface-to-air missile system represented a genuine advancement, with better range, altitude capability, and guidance systems. Fighter-based radar systems had evolved. Tactics had been refined based on decades of studying the problem. Yet there is no evidence that any of these improvements would have fundamentally changed the calculus against the SR-71. The aircraft's combination of altitude, speed, and reduced signature remained beyond the effective engagement envelope of Soviet systems. For the officers who had spent years attempting to defend against the Blackbird, its retirement must have brought mixed emotions. Relief, certainly, that the recurring demonstration of inadequacy would end, but perhaps also a grudging respect for the engineering achievement it represented, and an understanding that they had been participants in a technological competition where one side had achieved something genuinely remarkable. There exists in human history a recurring pattern. Barriers that seem absolute are proven permeable by those willing to invest sufficient ingenuity and resources. The sound barrier, once thought to impose fundamental limits on aircraft speed, was broken. The altitude ceiling that made the stratosphere seem unreachable became routine. The SR-71 represented an extreme expression of this pattern, an aircraft that operated in conditions so demanding that merely surviving the flight environment was an achievement, let alone performing complex reconnaissance missions while doing so. Soviet inability to counter the SR-71 was not primarily a failure of courage or dedication. Soviet engineers were talented, Soviet pilots were brave, Soviet resources were substantial. It was, rather, a demonstration that in specific domains, at specific moments in technological history, one system can achieve advantages that adversaries cannot quickly overcome regardless of their efforts. The margins of superiority the SR-71 enjoyed were sufficient that incremental improvements in Soviet capabilities, better radars, faster missiles, more capable interceptors, were inadequate. Closing the gap would have required fundamental breakthroughs in propulsion, materials, or physics that were not achievable within the time frame of the Cold War competition. The titanium skin that gave the SR-71 its high-temperature capability represented more than advanced metallurgy. It symbolized an approach to technological challenge that accepted enormous cost and risk in pursuit of decisive advantage. Every panel of that titanium skin, every rivet and weld, every system aboard the aircraft reflected thousands of hours of engineering effort, countless failed prototypes, and a willingness to persist through setbacks that would have terminated lesser programs. For those Soviet radar operators who watched their screens through cold northern nights, who tracked the faint echoes when they could, who reported contacts they knew would escape long before any response could be effective, for them, the reality was simpler and harder. The most sophisticated systems their nation could provide were insufficient. The aircraft that passed overhead, 16 miles high and moving at speeds that compressed time itself, represented a realm of technological capability they could observe, but not reach. It photographed their bases, mapped their defenses, and departed untouched, mission after mission, year after year. The freedom it represented was not merely political but physical. The freedom to operate in an environment so extreme that only extraordinary engineering could survive there. The freedom that comes from technological margins so substantial that adversaries are reduced to observing rather than contesting. It was a demonstration, repeated thousands of times across 3 decades, that in the vertical frontier of the stratosphere, there was a sovereign space where only one nation's aircraft could reliably operate, and all the radar arrays and missile batteries and interceptor squadrons deployed against it were, in the end, helpless witnesses to superiority they could not overcome. The contrail remained long after the aircraft had passed, a white line across the Arctic sky, slowly dissipating in the thin air, visible to those below as a reminder of what had just occurred beyond their reach. And then it too would fade, and there would be only the endless sweep of the radar screen, painting its green circle, waiting for the next contact that would come too fast to stop.